Hello and welcome to this video for CE108 Mechanics of Deformable Solids. So now we are moving to chapter 8 and we are going to talk about stress transformation. So in the previous videos and in the previous chapter that we have seen this quarter, so what we have seen is for different types of deformation, like for example for axial load and for torsion and for bending, for different types of deformation, we saw how to calculate the internal loads, internal shear, internal moment, etc. So all the internal forces and internal moments. And based on this and based on the geometry of the material, then we saw how to calculate the stress. So both the normal and the shear stress, depending on the types of deformation that you have. And so now, based on this, we are able to say if a material is going to break or not. And in this case, the condition is that a material is going to break if either the normal stress is exceeding the ultimate stress that the material can sustain, or if the shear stress in absolute value is exceeding the ultimate shear stress that the material can sustain. So now the question is, so far what we have seen is only one type of deformation at a time. So a pure torsion, a pure bending, or a pure axial load. So now the question is, if we have several types of loads that are combined together, in that case, you will also have several types of stresses that the material will be subjected to. And the question is, how does that impact the chance of the material to break? So what we are going to see now is that if you have a given material and this material is subjected to different types of stresses. So for example, if you have a given axis X and Y, and if you look in this axis and you have both, let's say, a normal stress on the x-axis, but maybe also a normal stress on the y-axis, and also potentially you may have a shear stress like this. So if you have the combination of all those stresses like this, how does it impact the chance of material to break? So that's the first question. And so far what we have seen is a way to calculate the stress along one direction, along the x direction or along the y direction. But what if we looked at the stress in another direction? So if we looked at the stress along some new direction, x prime and y prime. So if we do a rotation of the axis of coordinates, is the stress going to remain the same or not? And that's an important question, because if we calculate the stress in one direction, and then if the stress is changing along the direction, then we need to know how the stress depends on the direction, because we know that the material is going to break if the stress is exceeding a given threshold, which is the ultimate stress. So if the stress depends on the direction along which we are looking at, then the material may break. If there is at least one direction where the stress becomes large enough for the material to break, then the material is going to break in this direction. So in this case, we need to be able to predict how the stress is going to change according to the direction that we are looking at, to see in which direction is the stress maximum. And in this direction, is the stress large enough for the material to break? So that's what we are going to do in this chapter. We are going to see when you have different types of stresses combined together, and when you change the direction along which you are looking at the value of the stress, how does it affect the value of the stress? How does it affect the state of the stress? And in that case, in which direction is the stress maximum? And if so, is this stress large enough to cause the material to break along this direction? So let's see an example to see why would the stress depends on the direction along which we are looking at it. So let's consider a first example where you have a small element of surface, and let's assume that initially we look at the state of stress along one direction, which is in the original axis system X and Y. And let's assume that in this direction the stress is a state of pure shear, where, for example, you have a pure shear stress like this. So let's assume that you have a pure shear stress like this, where the only contribution to the stress is just a pure shear stress and there is no normal stress. So now the question is, what happens if I look now at the state of stress along a different direction? So if I do a rotation of the axis, so now I define a new coordinate system x prime y prime by doing a rotation of plus 45 degrees. So I rotate the axis, and now I want to know what is going to be the stress in this new direction. So if I want to do this, then I need to decompose the stresses that are applied within the axis coordinate system x and y, and to see what will be the new contribution, the new projection of those stresses on the new coordinate system. So here I'm just going to do it by hand without necessarily detailing the equation to do that. We are going to derive the equations on how we can transform the stress from one direction to another in the next slides. But for now, I'm just going to give you an idea of why the stress depends on the coordinate system. So if you take those stresses tau, and if you decompose them on the new coordinate x prime and y prime. So for example, like here you have a given stress tau. And now if I decompose it along the y prime and x prime axis, then I would have first a contribution like this along the y prime axis, and then a contribution like this along the x prime axis. So if I do the same for the other stress, I would have this stress here that can be decomposed into two contributions like this. This stresses that can be decomposed like this, and this stress component that can be decomposed like this. So now let's see what we get in the new coordinate axis x prime and y prime. So now what I'm going to do is just to redraw a small infinitesimal portion of the material, and now I'm going to draw this material along the x prime and y prime direction, and I want to see what will be the new stress along those directions. So if I look at now what will be the stress along those directions. So on the x prime axis, what are the contribution that I have? So first I have this contribution here and this contribution here. So if I add those two contributions, that is now going to give me a stress like this. So that's going to be the new stress in the x prime direction. So I will also have the same stress on the other side, because I know that necessarily this solid has to be at equilibrium. So if there is a force on the right, then has to be a force on the left. If I look at the stress on the y prime axis, now I would have this contribution here that's going to give me a stress like this, and we would have this contribution here which would give you a stress like this, so that the system is at equilibrium. So now if we look at what happened here, it means that in the original coordinate axis x and y, we had a state where the stress was a pure shear stress. So we had a state of pure shear where there was no normal stress. And now if we see what happens in the new coordinate system x prime y prime, after we had a rotation of plus 45 degrees of the axis, now there is no more shear stress, and now you have some normal stress. You have a state of compression on the y prime axis, and you have a state of tension along the x prime axis. So it means that now you have a state where you have some normal stresses. So it means that depending on the direction along which you are looking at the value of the stress, the state of the stress is going to change. You can go from a state of pure shear to a state of tension combined with compression if you just change the direction. So here, the forces that are applied to this solid are still exactly the same. The only thing that has changed is that now we change the direction along which we are calculating for the stress. And just by changing the direction, the state of the stress is changing. So why is it important? It's important because different types of material break for different reasons. For example, if you have a brittle material, then a brittle material typically break due to tension. So a material that is brittle, and some example of brittle material could be glass or concrete or other types of material that break in a catastrophic way. They break due to tension. So on the other hand, materials that are ductile, so ductile materials, they typically break due to shear. So in this case, the types of material, depending on the material a given body is made of, it's going to break either due to tension primarily if it's a brittle material, or due to shear if it's a ductile material. Example of ductile material would be steel, for example. So why is it important? Because it means that if you look in a given direction or another direction, depending on the direction that you are looking at, the stress can either be pure shear or can be pure normal stress. So that's important because if you have, for example, a ductile material, we say that this ductile material is going to primarily break due to a shear stress. So now if you calculate the stress along one direction, you find that there is no shear stress. There is only some normal stress, some compression and some tension. That doesn't mean that the material is not going to break, because if you change the direction, if you look in another direction, now there is possible that there is going to be some shear stress in this direction, and in that case the material is it's possible that this material is going to break in this direction if the shear stress becomes large enough and exceeds the ultimate shear stress that this material can sustain. On the other hand, if you look at if you have a brittle material and you look in a given direction and you find that there is no normal stress, again, that doesn't mean that the material is not going to break, because again, if you change the direction, then there might be some other direction where now you will have a state of tension. For example, in this case now, along this x-axis that is at 45 degrees, then you have a state of tension, which means that, again, if you have a tension, then it's possible that this brittle material is going to break. So we always need, whenever we have calculated the stress along one direction, if we want to know if the material is going to break or not, we need to be able to calculate the stress for every possible direction, for every rotation of the axis. Because if there is even one direction along which the stress becomes larger than the ultimate stress, then the material is going to break. So we need to be able to calculate in which direction is the shear stress or the normal stress becoming maximum, and that's going to give you the direction along which the material is the most likely to break. And depending on in this direction, if the stress becomes larger or not than the ultimate stress, then you can predict whether the material is going to break or not. So that's what we are going to do in this chapter. We are going to see, starting from a given state of stress. So if you know the state of stress in a given axis coordinate x and y, we are going to see some equation to calculate what would be the new state of stress after you change the direction of the axis. If you move to a new axis system, x prime, y prime, how does it change the state of stress? So if we are able to derive those equations, then it means that we can determine the state of stress for every direction. And if we can do that, then it means that we will be able to find the direction where the stress is maximum, which will allow us to find out if this material is going to break or not. So in this class, most of the problems that we have seen are in 2 dimensions. So in this case, the state of stress, that is to say all the possible values of the stress in 2 dimension can be represented as follow. If you take an infinitesimal portion of the body that you are considering, the state of stress consists in giving the value of the stress along x, the stress along y, and the shear stress. So in 2 dimension, you can have only those 3 shear stress. So sigma x, which is going to be like this, sigma y, and tau, where the positive convention for the stress is like this: normal stress positive if it's going out, and the shear stress is positive if it's going up on the right surface, down on the left surface, right on the top surface, or left on the bottom surface. So in this case, this is what happens if you look at the state of stress in a coordinate system x and y. So in what we are going to do in this chapter is to see how the state of stress depends on the direction along which we are looking at. And for this, we are going to assume that we are in plane stress condition. So what does it mean to be in plane stress condition? It means that we assume that there is no stress along the z direction, where the z direction would be coming towards you in this case. So if we are in plane stress condition, it means that there is at least one direction z where the normal stress along z and the shear stress along z, so there can be 2 shear stress along z, the tau xz and the tau yz, where, as a reminder, the first letter of those 2 letters here, the first one gives you the direction of the surface over which the stress is applied. So that's the direction that is orthogonal to the surface over which the stress is applied. And then the second letter gives you the direction of the force that correspond to this stress. So what we are going to assume is that we are in plane stress condition, and in plane stress condition, then the normal stress along z and the 2 shear stress along z, those 3 stress are equal to 0. That is the assumption. That's what we call the plane stress condition. There is at least one direction where this is true, that there is no normal stress and no shear stress. So we are going to assume that we are under those conditions for this chapter, and based on this we are going to derive, in this case, how does the state of stress in 2 dimension, which is only made of sigma x, sigma y, and tau, how does it depend on the direction of the axis coordinates. So in this chapter, what we're going to see is how does the stress changes if you do a given rotation of the axis. So in this case, since we will do some rotation of the axis, then necessarily there's going to be a lot of trigonometry relationships that are involved in those calculations. So I'm going to do here just a short reminder of the trigonometry relationship that are going to be useful for the rest of this video. So the relationship that we need to remember is, first, what happens if you want to calculate the cosinus of the sum of 2 angles. And in this case, if you want to calculate the cosinus of a plus b, then the relationship is that this is going to be equal to the cosinus of a times the cosinus of angle b minus the sinus of angle a times the sinus of angle b. The second relationship that is useful to remember is now what happens if you want to calculate the sinus of the sum of 2 angles. Then similarly, this is going to be equal to the cosinus of angle A times the sinus of angle B plus sinus of angle A cosinus of angle B. And the third relationship that is useful is the fact that the cosinus square of angle A plus sinus square of angle A, this is equal to 1. This is equal to unity. Now, based on those relationships, there is some other relationship that we can find that are special cases of those relationships. For example, if you use relation number 1, and if you assume that A equal B, then that allows you to calculate the cosinus of 2a. And so in that case, if you just apply a equal b, so that gives you cosinus square a minus sinus square a. And now if you use the equation number 3 to either transform the cosinus square into a sinus square or the sinus square into a cosinus square, then that gives you, for example, 2 cosinus square a minus 1, or you can also find another way to write this if you change the cosinus into a sinus, is that you can write this 1 minus 2 sinus square a. And so based on this, that gives you two important relationship, which is that now you can express the cosinus square and the sinus square in terms of cosinus 2a. So you can write that the cosinus square of a is equal to 1 plus cosinus 2a divided by 2. And on the other hand, you can also write the fact that sinus square a is equal to 1 minus cos 2a divided by 2. So why those relationships are important? Because it means that with those relationships, you can transform a cosinus square into simply a cosinus to the power 1, or sinus square to a cosinus. So those are important relationships because they allow you to linearize the equation, to transform an equation that was involving a cosinus to the power 2 to transform it into a cosinus to the power 1 to make this equation linear. Another equation that can be useful is, again, if you use now equation number 2 and you assume that a equals b, that allows you to calculate sinus 2a. And if you replace b by a, then that gives you that this is equal to 2 cosinus a sinus a. And so again, this allows you to linearize this equation, to transform a product of cosinus and sinus into simply a single sinus, which would be in this case sinus 2a divided by 2. So that's another way, again, to linearizing, to transform a product of cosinus and sinus into a single sinus. So those are the equations that we will be using in this chapter, which are going to be useful to derive the equation on how the stress depends on the direction. So now what we are going to do is to derive how the equation that will allow us to calculate how the stress depends on the direction. So for this, we are going to consider a small infinitesimal surface where we take a given material and we isolate a small portion of this material, and we take a small square of this material like this. We take a small portion of this material. So let's assume that we are choosing initially a portion of this material that is along the x and y direction. And so in this case, let's assume that the size of this infinitesimal surface are given by the dx. So dx is the length of this infinitesimal surface along the x-axis, and you have dy, which is the length of this infinitesimal surface along the y-axis. So along those axes, then we know the state of stress. So we are able to calculate this state of stress with all the equation that we have seen. So we know how to calculate the stress along the x direction, which is also going to be on the other side necessarily for this body to be at equilibrium. We know how to calculate the stress along the y direction, and we know how to calculate the shear stress. So we can calculate the shear stress tau, which is going to be like this. So now what we want to know is what will be the new state of stress if we change the direction. So now if we look at a new direction, x prime and y prime, after doing a rotation of the axis with an angle theta. So let's assume that we do a rotation of the axis with an angle theta. So we do a rotation, so now x becomes x prime and y becomes y prime after the same rotation theta. We want to be able to calculate after this rotation how will the stress change. We want to know if we start from sigma x, sigma y, and tau. This is the state of stress in the original axis x and y. We want to see how this stress is going to be transformed into a new stress sigma x prime, sigma y prime, and tau prime after a given rotation of the axis. So again, we are not changing anything in this system. We are not changing the material itself. We are not changing the shape of the body. We are not changing the direction of the forces that are applied on this body. We are just changing in which direction we are looking at. We are changing the direction along which we are measuring the stress, and we want to see how does it affect the value of the stress. So now, we want to transform. So what will be the new values of the stress? So what we are going to do to derive this equation is to isolate a small portion of this small square dx dy. And what we are going to do is to take a portion that looks like this, where I'm going to cut a fraction of this system here by taking a direction that is normal to the y prime direction. So that is in the same direction as the y prime direction. So here, if I look at this direction, here, this direction that is normal to the fraction that I'm isolating would be the same as the x prime direction. So I'm isolating this small fraction of this square here. So why do I do that? Because now, if I zoom on this new subfraction that I have just isolated, so I'm going to redraw it like this. So if I look at this small section here, then what do I have? If I look at the stress along this direction here, so now if I look at the stress that will be normal to this direction, the direction that is normal here to this direction is the direction x prime. So here what I will have is the stress along the x prime direction. If I look at the bottom here, this direction is still normal to the y-axis, so I would have the normal stress along the y direction here. And if I look at this direction here is still normal to the x-axis, so I will have the stress along the x direction. So here I still have the original shear stress, so I still have the shear stress tau along the x prime direction. But if I look at this direction, the stress that is going to be along this direction is going to be the new shear stress along the new axis coordinate x prime y prime. So now why did I do that? Because now if I can use the fact that this body, this small portion that I have isolated, due to the method of section, if this entire body is at equilibrium, then every subsection of this body also has to be at equilibrium, which means that this small triangle here has to be at equilibrium. And by expressing the fact that this triangle is at equilibrium, that is going to give me a relationship between the normal stress and the shear stress in the original coordinate x and y, and the new shear stress and the new normal stress along the new axis x prime, y prime, and tau prime. So that's going to give me a relationship between the new stress in x prime, y prime as a function of the old stress in the xy coordinate system. So if I want to write the fact that this body is at equilibrium, the equilibrium is based on the forces. A condition of equilibrium tells you that the sum of the forces is equal to 0. So far, what I have is the stress. So if I want to calculate the forces and not simply the stress, then since the stress is the force divided by the area over which the force is applied, I need to also know what is the area over which those stress are applied. So in this case, if I look at this, the very same portion again, So now I'm going to assume that this is a fraction that is also has a width along the z direction. So this is going to be not simply a square, but also a cube with a width dz along the z direction, where the z-axis is coming towards you. So if I look at this fraction, this portion here, it also has a width dz. So in this case here, if I look at all those lengths, so you still have here, this is dy, here this is dx, and so here you would have the length dz. So if I look at the value of those surfaces, so here if I say that this direction here is the new direction y prime, and this direction is x prime, while the initial direction was simply x and y, and in this case, so you have the angle theta here and the angle theta here, then I can find that this angle is also theta necessarily. This is, since this direction here is the same as this direction of the direction y prime, so I can see theta here. And in that case, we can find all the value that we need. So here, sorry, I made a mistake. This is not dx, because dx would be the original length like this. So now this length here is a little bit smaller, it's dl, and if I want to find the value of this length dl, then I can use some relationship, some trigonometry relationship. Why? So what I'm going to do is to call first, I'm going to say that this length here, I'm going to write it dy prime, so that's going to be the length along the new y prime direction. So if I do that, I can use some relationship to say that the cosinus of theta, I can express the cosinus of this angle theta. Cosinus is going to be the adjacent side divided by the hypotenuse of this triangle. So this is going to be equal to dy divided by dy prime. So that means that in that case, I can say that dy, the distance dy is equal to cosinus theta times dy prime. So I can also express the sinus of this angle theta, and the sinus of the angle theta is going to be equal to the opposite side, which is dl, divided by the longest side, which is still dy prime. So in this case, that gives me an expression to calculate dl, which is sinus theta times dy prime. And so based on this, now I can know, if I know the width dz and I know the value of those lengths, then now I can calculate the value of the surface over which the stress is applied. So now what I'm going to do is to write the condition of equilibrium for this small triangle. So I'm going to write the fact that this triangle has to be at equilibrium. And so we can first start, for example, by saying that the sum of the projection of the forces along the x prime axis, so the new x prime axis, which is this axis here, must be equal to 0. So let's do that. So the condition of equilibrium involves the forces. So we need to calculate the value of the forces associated to each of those stresses. So what do I have along the x prime axis? So first, we have the value of the stress here. So we have the stress along the x prime axis. So I'm going to say that the force along this x prime axis is given by the stress, which is sigma x prime, times the surface over which this stress is applied. And this surface is equal to the product of dy prime times dz. So that gives me the force, and in this case the force is directly along the x prime axis, and it's in the same direction along of the x prime axis, so its projection is positive. So now the second force that we have is going to be this force along the x-axis. So we have sigma x. Sigma x is along the x-axis. So what we need to do now is to find the projection of this force along the x prime axis. So this force is going towards the negative x. So it's going to have a negative projection along the x prime axis. So I will need a negative sign. The value of the force is going to be equal to the stress, so sigma x, times I need now to calculate the surface over which it is applied. So I am going to multiply the stress by the surface. So the surface is cosinus theta times dy prime. So this is the surface here. But I now need also to project this force, because this force is along the x-axis, but now I want to project it along the x prime axis. So in this case, there is this angle theta here between the x prime and the x-axis. So I need to do the projection. So in this case, if I want to project the force that is along the x-axis and to project it along the x prime axis, then I need to multiply this force by a cosinus theta, where in this case this comes from the projection. This cosinus theta comes from the projection. Okay, so sorry, I forgot a term here. So the surface is not simply cosinus dy prime. I also need dz to get the surface, and now I have cosinus theta, which comes for the projection. Okay, so we have the force along x. So what else do I need? Now I need to look at the force corresponding to sigma y. So sigma y is along the y-axis. If I project it again along the x-axis, this is going towards the negative x prime. So I will have a negative sign. So let's get the force first. So I get sigma y. I need to multiply it by the surface over which it is applied, which is dl times dz. So dl is sinus theta times dy prime times dz. And now I need to project this force along the x-axis, which is going to give me a sinus theta term due to the projection. Okay, so what else do we have? So if I look at this y prime force here, this y prime force, the tau prime force that is along the y prime direction, it's orthogonal to the x prime direction. So its projection will be 0 on the x prime direction. So I can neglect this force. Its projection onto the x prime direction is going to be 0. What else do I have? So I have this shear force here. So we have the shear force corresponding to this stress tau. So which is going to be, I'm going to start with this one first. So in this case, again, it's going to have a negative projection along the x-axis. Force is given by tau times the surface over which it is applied, which is cosinus theta times dy prime times dz. And I get a sinus theta when I project this force onto the x prime axis. And now I need to do the same for this force here. So again, this is going to have a negative projection along the x prime axis. The force is given by the stress tau times the surface over which it is applied, which is dl times dz. That is to say sinus theta dy prime dz. And in this case, I need to add a cosinus theta to project this force on the x prime axis. So since all of those forces have to be at equilibrium, then necessarily those forces, the projection of those forces equal to 0. Okay, so now let's try to condense a little bit this expression and to see what we get. So let's remember what we want to get. What we want to get is an expression of the new stress sigma x prime in terms of the old stress, which are sigma x, sigma y, and tau. So I'm going to isolate sigma x prime on one side. Here I can remove all the dy prime and the dz, I can divide everything by dy prime and by dz. And so if I summarize what I have, so the first term that I have is the terms that depend on sigma x, where I get sigma x cosinus square theta, and so I have removed all the dy prime and all the dz. Now I have the term in terms of sigma y, which is sigma y times sinus square theta, and we have the terms in terms of the tau, where we get 2 times tau sinus theta cosinus theta. So now this is where the trigonometry relationship that we previously reviewed are going to be useful, because now we have the term cosinus square theta, that when we can use the relationship that we previously saw to linearize this cosinus square. So I can rewrite this as sigma x times, so sigma x prime, this is equal to 1 plus cosinus 2 theta divided by 2. Then we have the term in sigma y, and I can linearize the sigma x prime, the sigma square of theta into 1 minus cosinus 2 theta divided by 2. And I can also linearize the product, sinus theta times cosinus theta. So here I have 2 cosinus theta times sinus theta, which is equal to sinus 2 theta. So this is equal to tau times sinus 2 theta. So now, based on this, I'm going to introduce to define some properties that are going to be useful in this chapter. I'm going to define, so this is a definition in this case. I'm going to define the average normal stress, which is going to be the average of the normal stress along the x and y direction, sigma x plus sigma y divided by 2. And I'm going to also define the difference in the normal stress, delta sigma, which is going to be the difference between the stress along x minus the stress along y. So in this case, this is a definition. I'm going to define those two terms like this. And so if I define this, then that I can rewrite sigma x prime, the new stress, the new normal stress along the x prime direction, as being, so if I look at the first term that I will have sigma x plus sigma y divided by 2, which is going to give me sigma average. And then the second term that I will have is sigma x times cosinus 2 theta divided by 2 minus sigma y times cosinus 2 theta divided by 2. So I can rewrite this as plus delta sigma divided by 2 cosinus 2 theta. And then I have the term in terms of the shear stress, so which is tau sinus 2 theta. So this is an important relationship because it allows me to transform the state of stress in the axis x and y, that is to say sigma x, sigma y, and tau. If you know those free stress, then you can use this relationship to calculate the new stress sigma x prime in the new direction x prime. So this is the relationship that allows me to do the stress transformation, to transform the stress in the coordinate x, y into the new stress in the new coordinate system x prime, y prime, after doing a rotation of the axis with an angle theta. So now, if we were to write the same condition of equilibrium, but by saying that the sum of the forces along the y prime axis is equal to 0, then what we would find is a relationship that can allow you to calculate the other stresses that we haven't talked about yet, which is the stress along the y direction, along the y prime direction, and the shear stress. So I'm not going to do that. I'm directly going to give you the relationship, but the idea would be still the same, to write the fact that the sum of the forces and the sum of the moment is equal to 0. So if I do that, I would get the following relationship, which is that now the new stress along the y prime direction would be sigma average minus delta sigma over 2 times cosinus 2 theta minus tau sinus 2 theta. So that's the relationship that we would get. One way to get this relationship is also to say that if I want the stress along the x prime direction, I can use the stress along the x prime direction and then do an additional rotation. So if you start with a given rotation theta, you get the x prime direction. And if you want to get now the stress along the y prime direction, you can do an additional rotation of an additional 90 degrees. Why? Because if you do a rotation theta and then you do an additional rotation of 90 degrees, then now the x prime axis would become the y prime axis if you do a rotation of 90 degrees. So if you transform theta into theta plus 90 degrees, then that would allow you to find the second relationship. And so we can also write the fact that the new shear stress in the new coordinate system is equal to minus delta sigma over 2 times sinus 2 theta plus theta plus tau times cosinus 2 theta. So those are important relationships because they allow you to calculate the new state of stress. So the new state of stress, sigma x prime, sigma y prime, and tau prime. And so that gives you the new state of stress in terms of the former state of stress. So this is the relationship that allows you to calculate the new values of the normal stress and shear stress in terms of sigma average and delta sigma. So in terms of sigma x and sigma y and tau. So if you know the state of stress, sigma x, sigma y, and tau, then you can calculate the new state of stress, sigma x prime, sigma y prime, and sigma tau. And so this new state of stress depends on the direction along which you are looking at. And when I say direction here, I mean what is the rotation theta? What is the angle of the rotation? So everything here depends on theta. Theta gives you the new direction along which you are looking at the stress. So depending on the value of theta, you define in which direction you are looking at the value of the stress, and that gives you the new value of the stress along this new direction theta. So this is what we will be calling the equation of stress transformation, because those are the equations that allows you to transform the stress from one direction to another direction.